In part two of portfolio performance, we will calculate the total return of Intel over its stock price history and then come to some conclusions saying that, well, if past performance is indicative of future performance, so in other words, if Intel has overperformed in the past, does that mean, we're going to assume that that's indicative of how we'll perform in the future? We can make some judgments as far as whether Intel is a good investment, a so-so investment, or a bad investment. In this slide, we want to talk about adjusted share prices and develop equation for adjusted share price. Now, remember that adjusted share price adjusts the actual share price for dividends and stock splits. And we're going to do a couple things differently. First, we're going to look at monthly compounding. Before we were looking at annual compounding, but now we want to do monthly. And we also, rather than calculating share price at the end of any given year, we want to calculate share price at the end of any given month. It could be month one, could be month 120. It doesn't matter. But we want to make those two changes because we're going to use those in the slides that follow. So the first section there is calculating actual share price. So what we want to do is we want to take a look at that table. S subscript 0 is actual share price now. S subscript T is actual share price at the end of month T. And remember that can be at the end of month 12, 24, 36, whatever. And then the next two variables are D and K. Now, D is the discrete time monthly dividend yield, and K is the discrete time monthly total return. In discrete time, we compound at the end of every period, whereas in continuous time, which we'll talk about, we compound continuously. But for our actual share price, we're going to use discrete time compounding. T equals time of month, and Z, capital Z, equals a cumulative stock price or stock split ratio. So this would be all of the stock splits over the time period now until time T. So if we take a look to the right, we have our actual stock price equation E1. That says that stock price at the end of any time T equals the stock price now times 1 plus K to the T power. So we're compounding monthly. And T is the number of months, times 1 minus D to the T power, times 1 over Z, and that's a cumulative stock split ratio. So that would be all the stock splits over the time period 0 to T. So our actual stock price equation is equation E1. What we want to do is we want to change that up a bit. In economics and finance, we typically work with continuous time. If you look at the Black-Scholes equation for option prices, that's a continuous time equation. And in continuous time, we compound continuously rather than once at the end of every period. Continuous time works for calculus. And the mathematics behind financial markets are calculus based. And as you know from your first year, or actually first class in calculus, that we need continuous equations. So if we take a look at the second table there, we're going to develop the equations for adjusted share price. Remember, adjusted share price, we don't have to worry about dividend yield. We don't have to worry about stock splits because all of that's taken into account in the time series on adjusted share prices, which we talked about in the previous slide. So we have A subscript 0. That's the actual share price now. Then A subscript T is the adjusted share price at the end of month T. And then kappa is a continuous time monthly or actual continuous time total return. That would be an annual return. And that's in continuous time. And notice that when we talk about discrete time, we typically use the regular alphabetic letters. But with continuous time calculations, we tend to use the Greek symbols. So rather than using K for discrete time monthly total return, we're using kappa, which is a continuous time total return, and that would be annual. And then we use small t, time in months. So if we go to the right there, that's the adjusted share price equation. And remember that for adjusted share price, we don't have to worry about dividends. We don't have to worry about splits. So therefore, none of that is part of that equation. The only thing we have to worry about is total return, and that is kappa. So you can see that in that equation. For continuous time, rather than using powers, we use the exponential function. And if you go into Excel, that's the EXP function. So rather than compounding monthly, we use continuous compounding, and we use the EXP function in Excel to do that. So what we're saying is E2 says that the adjusted share price at the end of any time t equals the share price now, the actual share price now, times the exponential of kappa times t. In this slide, we want to talk about linear regression. Linear regression is used by economists all the time. I remember in grad school, we used it all the time. But rather than explain what linear regression is here, what we're going to do is we're going to set up our problem and then explain what linear regression does in the next slide. But right now, we want to set up our problem. If equation E3, that's our equation for adjusted share price. We took that from the previous slide, and if you remember, that's adjusted share price at any time t equals share price now times the exponential of kappa times t, and kappa is the continuous time total return. Notice that equation E3 is not linear. And linear regression obviously needs linear equations, or at least performs better when those equations are linear. So what we want to do is we want to take equation E3 and convert it into a linear equivalent. The way we do that is we take the natural log of equation E3, and therefore we get equation E4. Basically, E3 written as a linear equation is E4, which says is that the natural log of my adjusted share price at the end of times t equals to the natural log of my share price now plus kappa times t. So now it's a linear equation. Now, for linear regression, what we want to do is we want to use linear regression to estimate equation E4. And what we're most interested in is that kappa figure, because that kappa figure is our total return, and that's what we want to calculate. So we want to set up our linear regression equation. So what we want to do is we want to say that the log of adjusted share price equals alpha, which is a constant, plus beta times t. Now the alpha is synonymous with the log of actual share price in equation E4, and the beta is synonymous with the kappa, which is the continuous time total return in equation E4. So when we run our equation, we're going to get values for alpha, and we're going to get a value for beta. Now the beta is what we want because that is the total return that the linear regression gives us. And remember that we're using adjusted share prices. So if you look at that time series snippet, here's a time series from Intel. Notice that we're going from month February 1st, 2023 to January 1st, 2024. And the second column there, that's the actual share price. And then the third column there is adjusted share price, which is equation E4. Which is equation E3. And notice that adjusted share price is different, especially as you go up that time series. It starts out at being equivalent. So at January 1st, 2024, we have actual and adjusted share price equals the same. $43.65. But as we go into that time series, notice that the adjusted share price changes and is now different from the actual share price because adjusted share price takes into account splits and dividends. And then we want to take the log, just like we did in equation E4, we want to take the log of adjusted share price, and that's the starting point for our linear regression problem. So what we did here is we took we went to Stuke, and we asked for all of the monthly adjusted share prices, and then ran it through our regression model. So what does linear regression do? If we take a look at that graph, the blue line is the log of stock price. It is that time series that we downloaded from Stuke graphically. So the blue line is the actual log of stock price. The red line is what the regression model estimates as a good equation for stock price over time. And what the linear regression does is that notice that that red line does not track perfectly with the blue line. Especially like in the middle there, we can see some big divergences. But as we move on towards the right, we see that those divergences are not as great. And what linear regression does is it says that I'm going to take the difference between that red line and the blue line. I'm going to square those differences and sum them up. Linear regression, what linear regression does is it minimizes that total sum of squares. So again, I'm going to take the red line, subtract out the blue line. I can take the difference between those two, square that value, sum them up, and that red line is the line that gives me the minimum sum of squared errors. So that's what regression does. So let's look at the regression results. We can look at the table to the right. Alpha value is negative 0.31. Beta value, which is our estimate of the monthly total return, is 0.01022. And remember, that's monthly. And the R squared tells us how good that model is as far as predicting the future. And at so R squareds go from 0 to 1, 1 being the best. So if the R squared was 1, that would basically say is that if we wanted to predict stock price into the future using that regression model, it would be a perfect match. But 0.79 is not perfect, but it's very close. So then we want to take a look at our total return results. The continuous time, and remember we're using log of stock price, so we're using continuous time. If we take that beta value of 0.01022 and multiply it by 12 to get an annual figure, we get 12.27% as a total return. But that's in continuous time. So what we want to do is convert that to discrete time. So we get 13.05%. So Intel has earned a discrete time total return over its stock price history of approximately 13.05%. Then we want to compare that number to its cost of capital or what the market expects. And the way we do that is we take the 10-year treasury rate of 4.71%, and that's the 10-year over, I think it's like 50 years, something like that. And then we want to take the equity risk premium, which is 4.75%, and we talked about this when we talked about valuation basics. Then we would want to take the equity beta, which is a measure of riskiness. Remember that beta of 1 says that the stock is as risky as the market. A beta less than 1 says that the stock is less risky. A beta more than 1 in this case means it's riskier or more volatile than the market as a whole. And we say that the equity beta for the industry is 1.49. So the way that we get the cost of capital, or what the market expects, is we take the 10-year treasury rate. We take so that's 4.71%, and then we add in the equity risk premium 4.75% times the equity beta of 1.49. So we get a cost of capital of 11.79. And you can see that Intel has earned, according to the regression model, Intel has earned a total return of 13.05%, but its cost of capital was less at 11.79%. And the R squared was 0.79, which means this is a very good estimator of stock price into the future. So we can make the conclusion that given that our regression total return of 13.05% is greater than our cost of capital, that our investment in Intel has performed better than expected. So it could indicate that this would be a good investment, in that if I expect to earn X, Intel is going to actually return X or something very close to it. So come join our community. It should be fun. We provide the software, all the calculations, all the historical data, everything that we've discussed in these slides, here and in the future. So come join us.